In this segment, we're going to talk about capillaries. All right, so in our capillaries, which connect our arteries to our veins, we have red blood cells, we have water, electrolytes, small molecules, large protein molecules, and the walls of the capillaries, the membranes that are the capillaries, are porous to glucose, O2, CO2. And not to the large proteins. All right, porous to electrolytes, porous to the water. Um, so permeable. Let me rephrase that. Permeable to these. They're permeable. And the red blood cells, we can get down in the really small ones. The capillaries are the same size as the red blood cells. They're squeezing through one at a time. So when we look at these, the concentration of proteins in the interstitial fluid out here is less than the concentration of protein in the blood flow. So inside the capillaries, 28 torr, outside 5 torr. These are the impermeants, right? These can't pass through, so they are the source of your osmotic pressure. Absolute pressure on the interstitial fluid is below atmosphere. It seems kind of surprising, but the tissue, no matter how soft, has some rigidity, and so it holds the interstitial fluid at below atmosphere. And so the driving pressure outside, which is the P0 minus pi 0 minus 6, right? We got our minus 6 minus another 5 is a minus 11 torr. All right, so let's think about this as we move along a capillary. On the artery side, we've got 25 torr of pressure. On the venous side, we've got 10 torr of pressure. There's this 28 torr of difference that's due to things that can't go through. All right, so let's just focus then on the driving pressure over here on this graph. On the artery side, the driving pressure that's moving water and solutes out of the capillaries is higher than the driving pressure on the in the interstitial fluid. So things flow from the capillaries out through them into the interstitial fluid. All right, you've got this net flow out. Then you hit this point where the pressure in the capillary, which is dropping all the way across here, right? As you go along the capillary, the pressure is dropping, drops below that, and then solute and water and solute starts to flow into the capillary. All right, so you've got things flowing out of the capillary until you cross over in the pressure, and then things start flowing back into the capillary. So this is you carrying nutrients out to your body. This is you bringing waste products and other things back to either get rid of or filter, right? When this balance is off, we get edema, right? We can get collection of fluid in the tissue. And in particular, if this crossover point moves over here to the right, we spend way less time getting in stuff flowing in and things flowing out. And how do we move that? Basically, we move this line up and down, right? Move this line up and down. What are some of the clinical problems that arise from this? Edema due to heart failure, right? So if your right heart is not doing its job, not pumping well enough, then what happens? The pressure rises on the venous side. And when the pressure rises on the venous side, right, this pressure goes up, then you're collecting fluid out in the body, right? And typically in the lower extremities. Why? Well, in the lower extremities is where your interstitial fluid pressure is going to be higher anyway because of gravity, right? So gravity makes your interstitial pressure a little higher, and because it's higher there, it's even harder to get fluid where you need for it to be, and to get fluid out. It's you've got so um, fluid buildup in the lower extremities because the venous pressure in the body is too high. Left heart failure, the pressure heading back into the heart again, back into the heart from the pulmonary system rises. and you begin collecting fluid in the lungs. You're not pulling fluid out of the lungs like you should. You're pushing it into the lungs and not pulling it back out. And you're when you have problems in your pulmonary system like this, you can literally drown on the fluid that your blood is pumping into the lungs. Nephrotic syndrome or liver disease, ascites, these are um, low protein content in the blood, right? So you have low protein content in the blood, and um, that changes these pressures, and you get fluid flowing the wrong way. I mean, you get fluid flowing out um, in ways you don't want. So you get too much stuff going on. You end up shedding a lot of fluid in this. Um, you can end up shedding fluid in the abdominal cavity as your liver basically leaks fluid. And it has to get rid of the fluid somehow. Your liver begins leaking fluid on its surface just to get rid of all the fluid that's being pumped into it. And that's uh, this is problematic, of course, right? And then um, nephrotic syndrome, nephrons in the kidney become permeable to protein, and that changes this whole dynamic again. Um, and when things go wrong with the kidneys, you end up peeing a lot of your fluid out, and you can dehydrate. And this is a, you know, classic issue for people that are becoming diabetic, is they're basically peeing out glucose, and so they're becoming dehydrated as they try and pee out all this glucose because the glucose is driving the fluid in a particular direction. Um, Edema and inflammatory reaction, and your capillaries dilate, fluids leak from the capillaries as the capillaries stretch, more fluid can go through them. Walls eventually become porous to white blood cells and move through the capillary wall. This is the kind of edema that's, we're trying to get white blood cells somewhere, usually, right? Um, this is a edema inflammatory reaction I have actually around my ankles if I get a sunburn down there, because again, gravitational pressure causes fluids to already be higher there. Um, all kinds of things happen around your feet um, because of that, because the pressure is not the same as you go into the lower extremities. Headaches and renal dialysis. So um, in the cerebral tissue, there's urea. As you remove it from the blood, you create pressure. You're always trying to your body's trying to keep the concentrations the same, and your concentration in the brain is dropping slower than it is in the blood. You're removing it from the blood. And so how does your body try, what's the fastest way for your body to even out the concentration? Pump water into the brain. All right. You can move the water much faster. You can move the urea. And so, you know, what does the body do? It pumps water into the brain in order to try and keep the concentrations balanced. Um, and that's problematic, right? And so you get these headaches, and this is why renal dialysis we take a long time, long time. We don't want to do that too quickly because um, you really throw some systems in the body off. Osmotic diuresis, right? I've already mentioned that. You increase urine output leads to dehydration. Osmotic fragility of red blood cells. This is a little different. This is a hereditary condition where the red blood cells are rounder and they absorb water more readily. And if the balance in the uh, electrolytes in the blood gets off, they can literally absorb enough water to pop. So somewhat problematic if you actually want your red blood cells. So all of this, all of this due to what is the balance of let me go back here. What is the balance of electrolytes, small molecules in the capillaries? How porous or how well how permeable are the capillaries to these? Um, what are the pressures everywhere, right? And when any of that goes off, when the concentrations go off, when the pressures go off, then you begin changing how this interaction happens as the capillaries go through and exchange blood or exchange fluids. Um, and that that throws any number of systems off, right? All right, that's it for part two.